Hi everybody, I'm going to talk a little bit about enolate alkylation in this video. So in the previous video, we saw kind of how to form enolates. Again, it's just down to basic acid-base, common acid-base chemistry. So for enolate alkylation, we're going to be looking at using enolates as a nucleophile in basically just SN2 reactions. So that's really all this is we're looking at SN2 reactions here, where we're going to be using enolates just as another nucleophile in our toolbox. So if I have cyclopentanone and I react that first with LDA, okay, so the first thing then is I'm going to look for my alpha protons. Okay, I've got two over here. So it doesn't really matter which side I grab. We're going to go ahead and form our enolate. So we're going to deprotonate that. And again, as we discussed in the last video, whenever you're using LDA, you're pretty much getting full conversion to that enolate, which is perfect for this, this type of reaction. So then we can just throw in whatever alkyl halide, epoxide, whatever kind of electrophile you want here. And that's going to be for step 2. So I'm going to throw in propyl bromide. So now we're going to use our newly formed enolate as our nucleophile, do our SN2 reaction. And then we formed a new CC bond. Okay, so our new bond that we formed is this guy right here. So we formed that alpha to carbon 1 bond. Okay, and again, harkening back to our SN2 days here. Alrighty, so let's go ahead and look at another example. So let's take a more complicated, a more complicated ketone here. So let's look at this guy. So in this situation, I again have 2 alpha positions, but they are no longer symmetric at this point. Okay, so I've got one situation where this H is definitely more hindered. And these ones are less hindered. Okay, so again, we need to be thinking about, kinetic and thermodynamic enolates here. So if I am using LDA again, I'm going to always have LDA going for the most accessible, the least hindered, to make my kinetic enolate. Okay, and then from that kinetic enolate, if we want to add in whatever kind of electrophile we want, in this case, let's go ahead and do an epoxide just for fun. Let me add in a methyl on there. So again, we're not changing any of the rules. We're still in basic conditions. So that basic conditions we're going to mean is going to mean that we're going to attack the least substituted side of that epoxide. So all of that is still, all that stuff is still relevant here, and we're not changing any of those rules. Okay, so we're going to end up with this, and then we can do an acid quench. And then we end up with our alkylated product. Okay, so another way you can do it is we really want to be having, again, that full conversion to our enolate. So another good option is to use a 1,3-dicarbonyl, because as we talked about, this proton is much, much more acidic. So if I'm doing something like this, I don't actually need to use something as strong as LDA. So I could use sodium ethoxide with ethanol. That's going to deprotonate my most acidic proton, form my enolate. And then this enolate, we can again throw in whatever kind of electrophile we want. We can throw in any kind of like alkyl halide, all that stuff. And again, we're focusing on kind of SN2 type things. So primary alkyl halides are going to work the best here. Okay, so we can get our alkylated product there as well. So just a couple of like overarching rules here. We're really looking at alkylation working better when we have 100% conversion to our enolate. Oops. Works best. So when you have full conversion to that enolate, that's going to work the best. Okay, so we don't want any of our carbonyl ketone remaining. And of course, in our non-enolate form. So we don't want any of that stuff remaining. Just so that we don't have any situations where we have multiple electrophiles in play at a time, right? So we want to make sure that we've got one nucleophile, one electrophile, and we want that to be our alkyl halide. So we want our enolate nucleophile, an alkyl halide / epoxide, electrophile only. Okay, so the best way to go about that is just make sure that you've got a large pKa difference between your starting whatever alpha proton you're using and your conjugate acid. Okay, so in this case, we did it by a couple of ways. The first way we did it is LDA. LDA is always going to be a good option. We do want to keep in mind that it does give us our kinetic enolates. But then another option is definitely to use a 1,3-dicarbonyl, and then you can use a milder base, but you still have a really big pKa difference, as we talked about in our first in our enolate formation video. So finally, I just want to talk a little bit about the synthesis here, just so that we're clear on how we want to break these down, knowing what we know now. So if we're looking at the retrosynthesis of an enolate alkylation, if I've got a ketone, so what I'm looking at here is I can really be forming this alpha to beta bond. So this one right here, and whichever side has your carbonyl on it, this side is going to be your nucleophile, and that's your enolate. And then this side is going to be your electrophile, and that's going to be your alkyl halide. Okay, so if we break this apart retrosynthetically, we're looking at this enolate, which is just the enolate of acetone in this case. And then we're going to have an alkyl halide. And the thing that's really, really important here, I know that we talk about counting your carbons and numbering your carbons a whole lot, But for some reason, for any of these enolate reactions, it's so easy to accidentally mess up and like cut off a carbon, add an extra carbon, whatever. But you got to be really careful here. And I always recommend to count them all out just to make sure that you are not missing anything. So we are going to put that as a large note here. Number your carbons. Okay, that stands for your entire life, but also like really make sure we focus on it for this. So if I was going to do the forward synthesis here, I would have acetone. I'm going to start off from making that enolate in full conversion. So step 1, we're going to throw in LDA. Step 2, we're going to add in our alkyl halide, which consists of our other 3 carbons. And then we're going to get out our, whoa, 1, 2, 3, 4. Our 6-membered chain with our ketone in it, okay, doing our alkylation reaction. All right, so as always, let me know if you have any questions, and I will see you all later.